Okay, the next thing we're talking about is variation. So we are going to have two major measures of variation, and a third that is related to one of those two. The first measure of variation is really not very informative. It is the range of the data. We've discussed the range of the data back when we talked in chapter 2 about finding class width. The range is the maximum value minus the minimum value. So let's go ahead and just compute the range for this brief little bit of information. These were the test scores that we saw when we were finding modes. So this data is not ordered, and it makes it harder to find a range in unordered data. So remember our stem and leaf plots we use to order our data, and ordering data is very, very helpful in actually finding ranges, medians, modes, etc. So we have to look through this carefully, and we have to find what our biggest point is. Well, there's our biggest one, and then it's a little bit harder even to find the smallest one, and the smallest data point looks to be this 39. So I'm going to circle it as well and then look through again. Nope, that looks like the smallest one. So my range of data here is 100 minus 39. And so this is going to give us 61. And 61 is the range. Now that is the spread of the data from the smallest point to the largest point. How much range does it have? Exactly what it says it is. And that can be quite informative or not so much. So range is not that great for us. The important measure of variation that we have is called the variance. The variance is the average squared deviations about the mean. So this is measuring in comparison to one of our measures of center. Squared deviations, that's important, okay? When I say squared deviations, you should know, oh, that has some significance. And that significance is, of course, that it's always going to be positive, right? Because we square these things. So variance is always positive. And then the other thing that we're looking at is it's the average squared deviations, and that's why we square it, because if it was just average deviation and we had a fairly symmetric data set, there would be no deviation about the mean. The deviation would be 0 because some would be above and some would be below. So it'd end up being 0, and that is indeed why we end up squaring it to find the average. So we have the average squared deviations about the mean. Now we have two different cases. We have for samples and we have for populations, and we have our own notation for each of them. For samples, again, English letters. For populations, Greek letters. So the sample variance is called S squared, and the population variance is called sigma squared. This thing, it kind of looks like a loopy R, and that's a lowercase sigma. We saw the uppercase sigma right here. Remember, that means the sum in math and science. But this lowercase sigma squared is our population variance. Now the two formulas that I'm giving you right here, these are what we call the defining form of the formula, or defining formula. We don't want to use these, but they are very good at showing us the definition of the variance, hence the term defining form. So this says I'm going to add up all of the x values, each of the individual data points, subtract the mean. So how far are they from the mean? And then I'm squaring it. Squared deviations about the mean, right? So how far does each data point deviate from the mean? I square it, and then I add it all up and I average it. Now, you see this is n minus 1. Averages, right, we say the number of data points. Well, this is deviations from a certain point in time. So it's just like taking a number line. If I were going to divide a number line from 0 to 1 into quarters, how many lines do I use to break it into quarters? Well, I use 3 lines to divide it into quarters, because I'm breaking this one whole thing up into 4 positions. I use one less number. The same sort of thing here, one less because we're deviating about a fixed point. So average deviations about the mean, and that's what the defining formula is good for. Down here with the population variance, we're looking at the values in the population, that's what X stands for, minus the population mean squared, so how much does it deviate from the mean, square it, and then we have to add them all up, and then we are dividing by the population size. So again, variance, one of the reasons we like it is because it is an unbiased estimator. Variance, however, we don't like so much because variance has squared units. And I don't know about you, but I'm not real sure what a squared year is or a squared minute or some of these things that are a little bit more confusing. And that's why we have the next one we'll talk about with this, which is a standard deviation, which is just the square root of the variance. So let's figure out the variance first, then we'll talk about the standard deviation. So most of the time, again, we're going to be talking about sample variances. Every once in a while you'll do population variance. Now it should be noted at this time, and I'll note it again, your calculator gives you both the standard deviation and for the sample and the population, because your calculator's stupid. It doesn't know which it is. Is this a population? Is it a sample? You decide that information and you'll choose which one to use. So with that said, let's go ahead and look at the other formula. And this is the formula that we do want to use. These are the computational formulas for the variance, sample, and population. Notice again down here just the capital N versus N times N minus 1. Now this doesn't quite look like the other one, but algebraically these are absolutely 100% equivalent to one another. So it can be mathematically proven, but at this point in time we don't need to do that. So we're going to use this formula to compute the variance. And it may look really very confusing to you, but it's actually quite easy. All we need to compute this thing is n, which we all know to be sample size. We'll need the sum of the x squareds. We'll talk about what those are. And we'll need the sum of the x's, which we've already used in our mean, and we'll get to square that. And we're just going to plug into this. It's a formula. So let's do this for the purse snatcher data. So here's the purse snatcher data again, and we know that the sample size for purse snatcher was 10. We had already found the sum of the x's, remember, using our calculator, and we'd found that to be 298. Now the sum of the x squareds, these things are exactly what they say they are. They x squareds and then they're summed. So what this means is it's going to take the 16 and square it. And then it's going to take the 17 and it's going to square it. And then it's going to take the 21 and square it, and the 25 and square it. And it's going to go so on and so forth all the way down until it has 50, and it's going to square it. Now if we had to actually go and do that, that would be quite a process, wouldn't it? But you know what? Our calculator actually gives this as part of the one variable statistics. So when we ask for one variable stats, like I have already shown you how to do, we are actually going to have that value available to us. And the value for the purse snatcher data for the sum of the x squares is, let me get it up here again, it is 9,954. So this is 9954. And that is the value right under the sum of the x's. So when you look at your calculator, you'll see x bar first, and then you'll see the sum of the x's, and then the next one listed is the sum of the x's, sum of the x squareds. So now we have everything that we need to put into this computational formula. So we're going to be calculating s squared, got to get the right notation, it's a sample, and it's the variance, so we put s squared. And then we're going to write down our n, which is 10, and then we're going to write down our sum of our x squareds. Now we want to make sure that we get the right value in here. We want to make sure that we put the sum of the x squared value first, and then minus, and then we're going to put a sum of our x value in, and we're going to square that. So that's 298, and it's going to get squared. And then down here in the denominator, we're going to put our n, and then in parentheses, we're going to put our n minus 1. So 10 minus 1, which is 9. Now, I'm going to ask that you actually write everything out for me. So we're going to write 10 times 9,954. So that's going to be 99,540 minus, then we're going to square 298, and we're going to get 88,804 out of that. And then in the denominator, 9 times 10, which is 90, one more time here. We're going to subtract 99,540 and the answer that we just got of 88,804. So this is going to give us, and we're going to write it down, 10736, and we're going to divide by 90. And then we're going to write that value down. Now this value I'm going to write out as an approximation still, so approximately equal to, and I'm going to write it out to 6 decimal places, because then if I ever need it to calculate, I've got it written down for myself. And I will show you why we will need it to calculate in some points in time. So 119, 2888, and it keeps going. So I'm going to write 28888, and then I'm going to round to 6 decimals. So see 2, 4, and 6. Now, the way that we report, okay, this is what I'm writing down for myself, and then I'm going to report one more decimal than the original data. So see, my original data is in the ones, right? So that's the smallest place value. So I'm going to round to the nearest tenth. So I'm going to report this as 119 point, and then the point is going to be 0.3. And these are years squared. And this is the problem with this. Even though it's an unbiased estimator, years squared doesn't make a whole lot of sense. So I don't know what to do with it. So years squared. And that's my variance for my sample of purse snatchers. Now, years squared doesn't make any sense, so what we want is the standard deviation. And the standard deviation is nothing more than the square root of the variance. So the standard deviation, S we call it for the sample, is the square root of S squared. But in order to get the exact answer, we need to take the square root of the exact standard deviation. So the exact standard deviation was 119.2 888888888, so on and so forth, right? So I want to take the square root of that answer, and that is going to get me approximately, and again I want to report that to 6 decimal places at least, 10.9219459 if I wanted to go out that far, but I'm just going to round it to there. And then I'm going to report, again, this is for me, right? And this is to report, I'm going to report one more decimal than the original data, 10.9, and these are in years. Now what I'd like you to do is I would like you to take 10.9 and I'd like you to square it. And I'd like you to take the square root of 119.3. And then I want you to compare those to the two values. This one here for this, and then with this one back to this value here. So this value here, compare it back here and see what you get. And if we square 10.9, oops, we square 10.9, what you get is 118.81. Now how does that compare to 119.2888? Not the same, right? So because this doesn't equal what the actual variance was, that's why we need to have this, because if you square 10.9 21945, what you get is 219.28888, and it doesn't keep going eights, but it's close. And the same thing you're going to see here. It's not going to compare to this. So I have to stop now, but you should do that on your own.